Okay, hi everyone. So I'm sure most of you have data pipelines, right? I mean, who doesn't these days? And we're also in PyData, right? And I'm also sure most of you have experienced high loads on your system, heavy queues, right? So today we'll talk about how we supercharged our pipeline efficiency using machine learning performance prediction. My name is Keren Meron. I'm a software engineer at Singular.
And I'm Boaz Wiesner. I'm a DevOps engineer at Singular.
So what do we do at Singular? Our clients are companies who need to pull their marketing data from various different sources. They're very granular and complex data, and combine it into one table. And at Singular, we do just that. We pull ad campaign insights from over 1,000 data sources, process it through a complex pipeline, and then provide our clients with full return on investment insights, ROI, on their marketing efforts. Additionally, we're also an attribution provider. This means that we track events reported to us from our clients' apps and connect them to the ad which caused the user to install that app. This allows us together to supply our clients with very granular return on investment information. For example, what is their ROI for a very specific creative? So our data pipeline has numerous different tasks which pull, process, and store our clients' data. Each server in our data pipeline has dedicated workers which run specific tasks, which are logically grouped. For example, all tasks pulling and pushing data to our Snowflake database are grouped under the Snowflake label, and then there are dedicated workers which run all of these tasks. Our data pipeline workers are Celery workers. Celery is a task queue implementation used to execute tasks asynchronously. And these workers are managed by Kubernetes. Kubernetes, it's a container platform used for managing deployment, scaling, and management of containerized applications. It's important to note that our clients rely on their data from us in a timely manner. So they come to work at 8 in the morning, and they log into Singular to view, analyze, and make marketing decisions based on their data. So if their data isn't ready on time, they can't do their job. And this is true throughout the day while we supply them with their real-time data. So what's our problem? Why are we even here talking today? Well, we noticed that in our pipeline, we have different tasks with very different characteristics in terms of duration and required memory. In fact, we saw that over 90% of our tasks are very light tasks, while around 10% of our tasks are heavy tasks. Well, what we saw is when we investigated accumulating queues, that sometimes the task will be running for a very, very long time, and then many short tasks will be stuck after it in queues, like you can see here. And then the result of this is that smaller clients were being affected by bigger clients because their tasks otherwise would have taken a very short time to run. Another interesting thing which we noticed is that Celery prefetches the next task to run while running the current task. This means that if a task is running for a very long time, and we have automated processes which will kill a task that's running, say, for over 24 hours to avoid stuck tasks, then the next task, which statistically would be a short task and was prefetched, would just disappear. So how do we solve this resource contention? Well, the first thing we can do is manually scale our workers. This is a great catch-all solution, but it's not sustainable because we'd have to increase and decrease our workers all the time. And it's expensive, and it would increase our cloud spend. Another thing we could do is split our tasks into smaller tasks, which is a great design solution, but sometimes it's very complex to do. For example, if we have a task which pulls data from Facebook's API for a certain time range, and we've already reduced that to 1 day of data, we can't reduce it anymore and our hands are tied. So finally, we realized what we need to do is have better resource management, meaning split our workload between light tasks and heavy tasks so that then we can optimize each group appropriately. Once we've done that, then one of the things we could do is use auto-scaling for the group of light tasks, and we'll speak more about that later on. So how do we do this? How are we going to differentiate between our light tasks and our heavy tasks? Now, you could tell me, okay, what's the problem? Let's just take task A, tag it as light, task B, tag it as heavy according to the task characteristics. And then maybe you have a few input parameters to the task, so we can maybe define some static function which will take all of these parameters and their values and output the tag for the task. Now, the problem with this is, first of all, we have a long list of parameters, very long, so it makes it even more difficult. And also a very long list of possible values as input for these parameters. And the variance of them is very high. Additionally, our tasks in Celery are chained together. This means that the output of one task is the input to the next task. And then if the number of rows is affecting the time it takes our tasks to run, then this is another dynamic parameter, which is really configured during runtime, and we can't know ahead of time to use for this static function. So how are we going to solve this classification problem after all? Well, we decided to use machine learning. So we tried out a different types of models, trained them, and saw which one gave us the best results. This was a fairly simple model, the SVR, support vector regression. This is a supervised learning algorithm used to predict discrete values. And what it does is try to find a hyperplane in an n-dimensional space, which fits the maximum number of data points. The advantage of this algorithm is that it's robust to outliers, it works well in high dimension, and it's fairly easy to implement. Now, this is very important since we want to productionize our model. Some disadvantages are that it doesn't work well with noise, and that it's not very suitable for large data sets because it takes a long time to train. Now, again, this could be pretty good for research purposes, but not when we want to have our model training in production. Now here you can see that we set up a configuration for each one of our tasks for the SVR model. Here, for example, is the scrape customer task, which pulls data for our customers. And you can see we've set up the parameters for the model, the kernel, C, gamma, and epsilon parameters, and which features we'll be using. So here are the number of days and number of accounts which we're pulling data for. And finally, we have the ID parameter names as customer ID. This means that we decided to split up our model into one model per customer. We started out with one model for all customers, but then we saw that the training wasn't performing very well because the data of each customer is very different from each other. So that's why we decided to split it up. And since the models came out to be fairly small, this was fine in terms of saving the model. Now, we saw in the previous slide the features which we were using. How did we reach these features? Well, we started out with a long list of parameters which can be input to our tasks. Here's a few of them. And then we experimented with different combinations while training the model and saw which had the most significant impact. Now, once we productionized our model, we started seeing some tasks which were tagged wrongly. So a task would be tagged as a light task, but then would take a long time to run, and then again cause queues. Not very good. So we investigated, and what we saw is there was a parameter that we didn't take into account as a feature. This is the account parameter. What is an account? Some of our big clients have a lot of apps, so they split them logically under accounts. And in Singular, we do something similar. For each task which pulls data for a customer, we won't pull all its data. We'll pull it for a certain number of accounts, but it can be 1, 3, 5, 10, 20, and changing each time, and the combination will be different each time as well. So it's not a set group of accounts. So how do we take this account and use it as a feature? The first naive solution would be to just take all permutations of the account ID, but now the account ID is a number, but it has no numerical significance. So this wouldn't work well as a feature to a model. The next thing we thought of doing was taking the total size of the account, which means what is the spend allocated for the account by the customer. This is another not so good solution because we could have one row of data with $1,000 spend, or we could have 1,000 rows of data with a total sum of $10 spent. And since the time it takes for a task to run is affected by the amount of data, the granularity of the data that it's processing, then this wouldn't work very well. So then we realized what we really need is the expected row count. But since we're pulling data from third-party sources, we can't know how much ahead of time we're going to pull. So what we do is we can check historically in our databases how much we've pulled in the past for this account and use that as the feature. Okay, so now Boaz will tell us a bit more how we productionized the model.
Cool, thanks, Keren. So Boaz, ops guy. So the most important thing when we productionalized our model was the fact that the model performance had to be high quality and consistently. Since now, like in the case where we have, for instance, a heavy task that we classified into a light task queue because of some kind of incorrect prediction, then we'd kind of just like all the machine learning in the world wouldn't help that, right? Like we're back at square one. We've done nothing. So it's really important that we classify things correctly. Now, in order to make sure that this happens, we have a periodic task called the performance predictor tester that basically runs and checks for deviations between our predicted task duration in memory and the actual task duration in memory. It does this using RMSE, or root mean square error, and it just goes over a number of points in a time window and does the root mean square and finds the deviation between them. And as you can see, we have here example output of like a deviation of around, I think it's around 7 or 8 minutes, which is okay for this class of tasks. The second most important thing while productionizing this model is that you need to have the model trained beforehand, right? And then when the task actually shows up and you want to classify it, you need to be able to run it quickly and efficiently. The way that we do this is at the end of every Celery task, we have a custom class called the task info collector that collects task metadata, such as runtime or memory, and pushes it into our custom metrics in Datadog. But also we added an additional flow that pushes it into S3. And it takes the relevant information for performance prediction and puts it in S3, where then, while it's sitting in S3, which is AWS's object storage, we can query it using Amazon Athena, which is AWS's SQL service that allows you to query data over S3. And that's kind of exactly what we do, because then we have the performance predictor train runner, which is a periodic task that we run about once a day, and it does all the heavy work. It takes the data from today or from the past days from S3. It trains it based on the existing model. And then once it's done training that information, again, per customer, right? It pushes it into a Redis database where it's stored with a key of the customer ID, and the value is the entire model, serialized, right? But just the entire model sitting in Redis. And then finally, the last piece of the puzzle is the Celery router, which is a piece of the Celery infrastructure where when every task in Celery gets to it, the router can decide where and which task to send, which queue to send the task. And we implemented custom logic in the Celery router to query the Redis with the right key, get the model, run the task through the model, get the classification, and then based on that split to the correct queue. And that's exactly what we do. We split into light and heavy queues. We're able to dedicate specific Celery workers for each type of queue. And we've solved our problem of resource contention. There's no more snowballing task buildup. And most importantly, no data delay for smaller customers that are caused by bigger customers. So now that we've done that, we can jump a bit into the concept of autoscaling, right? So autoscaling in general is the ability to increase and decrease capacity based on real-time parameters. Essentially, when we're under heavy load, then we can scale up our systems. When that load is done, then we can decrease our capacity. And in Celery, this translates directly into scaling the number of workers up or down. So in general, why bother with autoscaling? Well, aside from the fact that it's 2022 and should be autoscaling everything by now, and the fact that I'm a DevOps guy and I love seeing autoscaling graphs just makes me happy inside. But putting that to the side, the important thing is that it reduces queues. It increases multi-tenancy and resource utilization, where multi-tenancy is where you can have multiple workloads running on a shared infrastructure, because when one workload is under fire, then the other one isn't necessarily, and therefore they can kind of sit on the same thing and it works. And there's also very important, no manual intervention necessary. There's no more waking up in the middle of the night, engineer clicking the plus button so that the queues go down. Now, autoscaling Kubernetes and Celery is a little bit different than classical autoscaling, where, for instance, if you have a web server and it's running hot on CPU and running out of CPU or memory, then you're like, okay, well, I'll just I see that the CPU memory is high and I'll spin up a new server and that's it. So here our load is defined by queue length, right? We would like to autoscale based on the length of the queue. Now, another important thing is, since one of the axioms of our data pipeline is to not interrupt long-running tasks because it would be very costly to rerun them, then we in our case, then scaling is really only efficient with smaller tasks, because if you were to scale up a large task and you wouldn't interrupt it, then you couldn't scale it down simply. You wouldn't be able to scale it down because you wouldn't want to interrupt it, and it would just be stuck there, and you'd gain nothing really from autoscaling. You'd scale up and be stuck. So how do we actually autoscale? So we do this using Kubernetes, and you can see our infrastructure here in the top left. There's the Kubernetes worker node, which has the horizontal pod autoscaler. This is the component that is responsible for actually doing the autoscaling, right? In our cluster, then one pod is one Celery worker, one container, and the HPA is responsible for scaling, is actually deciding how many things there are. If there are 200 workers, 1 worker, 15 workers, it's what actually does the scaling action. And as we said, we want this to be based on the queue length. So since we use Datadog for all of our internal metrics, then we'd like to get this from Datadog. And for that, we have our Datadog cluster agent. And that's exactly what it does is it takes the metric from Datadog and makes it available in Kubernetes using the Datadog metric CRD, or custom resource definition, which is basically Kubernetes' way of taking external things and making them available through Kubernetes API. And then we're able to hook the horizontal pod autoscaler into that metric and scale based on queue length. Now, the 2 final components are the vertical pod autoscaler that defines the resource requirements for each worker. And this is important because let's say the horizontal pod autoscaler wants to scale up to 20 workers, and each one of those workers requires a gig of memory. We may not have enough capacity to deal with that at that moment, and the pod would be marked as unscheduled by Kubernetes. So in order to solve that, we have the final component in the bottom in the system node, the cluster autoscaler, and it waits for these unscheduled pods, sees when they exist. If they exist for a certain period of time, it chooses to scale up a new server, and then that new server can handle that additional capacity. And here you can see our actual metrics. This is taken straight from Datadog. And the sharp of eye will notice that the metric used by autoscaler is a moving rollup on the queue length. This is interesting because queue length is a relatively spiky metric, and what that would cause is needless scaling up and scaling down. So doing a moving rollup, which is averaging out the values within a rolling time frame, is efficient here and helps us kind of smooth things out and just have everything scale and work smoothly. And on the bottom, you can see the number of running pods. And I think the correlation there is very clear. Queue goes up, number of pods goes up. Queue goes down, number of pods go down. And it's interesting to note that it's reactive, right? The queue goes up and only then afterwards the pods go up. And this is kind of an inherent constraint of scaling based on queue length. So another great thing that we can do now that we're auto-scaling and we've separated all our tasks into short tasks is some cost optimization and utilize AWS's spot instances, where spot instances are AWS spare compute capacity that you can purchase at a fraction of the cost, with the one added caveat that they can interrupt you with a 3 or 4 minute warning, right? So since now we have resilient infrastructure due to auto-scaling and we have short running tasks that we don't care if they're interrupted, we can use these spot instances and really reduce our cloud spend. So cool. So kind of to summarize everything, because we went through a lot, we started with the problem where queues and resource contention were causing issues in production. We had large tasks that were causing small tasks to be stuck and causing data delay for customers. We checked a couple of options and looked through different possibilities and decided in the end to use machine learning to predict task performance and split our tasks into light and heavy queues. And once they were split into light and heavy queues with dedicated workers, we were able to auto-scale these light queues with Kubernetes and further increase resource utilization. So what does the future hold? So one interesting possibility is to implement an auto-scaling predictor, since now we're working reactively, but we know for a fact our pipeline tends to have trends of scaling up and down throughout the day. So if we could train a model that would learn to predict this or implement something that already exists that does this, we would be able to scale based on queue length patterns and not just on queue length. And secondly, in general, this is up to you guys. Let us know, right? But we think that the concept of machine learning based routing is pretty cool and interesting. And if there's general interest, then reach out, let us know. We may even think about generalizing it. So thank you so much for listening. And yeah, our mail's up here if you want to send us any questions in the future. But as for now, Keren and I are here to answer anything. Yeah.
What's your retraining policy, like your retraining strategy when reaching out to new tenant is arriving, new customer coming out? How does your model predict the new lead data, and how do you make it robust enough for future case? Yeah.
So when we have a new customer, a new thing, then we can set specific, we can set for each task if it's in a learning state or if it's in a predictive state. And then based on that, we're able to do it.
Yeah, but it's true that for a new customer, since they don't have a model yet, then they don't gain from having a trained model. And then we know that in the first days, then we might get, if we use a model, we might get wrong predictions because we don't have data for this customer yet. So what we do is sort of assume, we're going to assume and direct them to a long queue, like a heavy queue, so that we don't affect the short queues and the workers in the auto scaling. And then once we have a few days of data, then it'll start working correctly.
Okay, and how about when an API changes? For example, from now on, Facebook added a new, I don't know, JSON, huge JSON for one of the data sources. And now your current clients will get the wrong prediction somehow. How do you monitor this? How do you understand what's going on? Do you have a retraining strategy in place? That's what I'm asking.
Right.
Yeah, look, as part of when we had the as part of our infrastructure, right? We retrain the model essentially every day, right? We periodically retrain the model every day. That's the task performance train runner. So that runs periodically every day to retrain, also based on new data from today and what's currently existing. So if something were to change, it would pick up on that, right?
Mm-hmm.
Yeah.
Do you guys consider a serverless architecture like like AWS Lambda, for example?
Yeah, so our pipeline kind of runs at a scale where that would just burn a hole in our pockets. But you mean in the sense of specifically the running like the machine learning on it, or running?
No, I mean, as far as I know, in AWS Lambda, you don't need to tell ahead of how much resources you need. You just put it in the...
Yeah, so it's mostly just way too expensive for the scale we're running at.
Yeah. Do you consider using more than 2 queues? And how easy it would be to split it to like 5 different queues?
Yeah, so that would be really the next step, since our prediction today, what it does is just predict based on a threshold. So we get the predicted memory or the predicted duration, not a tag, and then we have a threshold. So we could easily define 2, 3, or 4 thresholds and then just have as many queues as we would like. Mm-hmm. Yeah.
What's your time latency between delivering the model and it's served?
It's pretty instantaneous now, because it's pushed into Redis, and then on every new task getting to the Celery router, the Celery router queries the Redis to get the new model, right? So there's very low latency there.
Yeah, and the models are pretty small because we split them up per customer. So that's really like the training and the saving to Redis is really instantaneous.
And the time it takes the Celery to model and...
The routing? Yeah, the routing as well. So all the routing does is query the model and then run the next task through it. So this is even shorter. It's very quick, and it's important because we don't want the routing to take a long time, right? So we made sure, and that's pretty instantaneous, yeah.
You mentioned that you did a different model for each client because of differences, but is there, despite that, is there maybe like some common ground that can be used? Like in a general sense, you consider somehow trends across all clients and not making it up per client?
Yeah, so we do have groups of small clients based on their amount of data, and we could group the clients based on that. It's an interesting point. We didn't do it just because when we started out, we wanted to start out pretty simple and see that works and then move ahead. But definitely, and also another thing, there are other things to take into account. For example, environment, things happening in our environment, in our system now that could have effect. So there are many more things to do to advance this and change the model. Yeah. Any other questions? Okay, so yeah.
Last one. You'll have to shout. We can't hear. Yeah. Yeah, sorry. So I threw that word around a lot. Datadog is a SaaS service that basically works as for metrics. It's for monitoring and metrics, and they do APM and logs and just about everything. So all of your monitoring, it's just a SaaS solution for monitoring. Kind of if you know New Relic, if you know even Prometheus Grafana, those kinds of things.
Okay. Thank you very much.
Thank you, everyone.